Hello guys, today we'll be focusing on acceleration and its two components. So the two components of acceleration that I have with me will be the normal, okay, and we will have the tangent. So these are the two components of acceleration that we will be studying. These two components of acceleration are very important and are vital in determining the design of many engineering models such as a curved highway. Okay. However, before I go into detail into acceleration, the normal and the tangent components of an acceleration vector, I will need to look at some of the very basic things such as curvature. I need to look at length of an arc. I need to look at tangent vector. I need to look at normal vector. I need to look at binormal vector, oscillating plane, and all these things. Okay. So the first part of this video will actually focus on these basic things, and the second part of the video will build up on these basic things and go on and discuss how these things can help us understand normal and the tangent components of the acceleration vector. Okay, so let's go on and let's study the arc length. Okay, the arc length. So let us consider we are having a vector, a position vector R. Okay, this position vector is given by x of t in the I component plus y of t in the j component plus z of t in the k component. Okay. Now, I want to find the velocity vector. The velocity vector, or in other terms, I can say the differentiation or the prime of the position vector. So I'll write here, or you can say r prime, will differentiate each term separately. So dx over dt as the I component plus dy over dt as the j component plus dz over dt as the k component. Perfect. Now let's go ahead and let me say what is the arc length. Now let me define the arc length. Okay, the arc length is actually equal to, let's say arc length is denoted by s from the points A to B, from the parameters A to B, is the magnitude of the r prime, and we integrate with respect to dt. Perfect. Okay, guys. Now let's see. From here we can find another very important formula. If we differentiate both the sides, we will get ds over dt is actually equal to the magnitude of r prime, and we can also say it is also equal to the magnitude of the velocity, which is the speed. So we have these formula with us. Now let's go ahead and let's actually look what's the use of the arc length. So guys, let's say I have a helix. Okay. I have a circular helix, and the helix is given by this formula. My helix is given by this formula right here. So cos of t as the I component, sine of t as the j component, and just t as the k component. Now I need to reparameterize it. So why do we need to reparameterize a certain vector function? This is because whenever we reparameterize a certain vector function, what happens is that particular equation is actually independent of the coordinate system. So it means it is independent of whether it is in the Cartesian system or whether it is in the coordinate system. So let us first of all find r prime. So r prime is actually equal to negative sine of t plus cos of t plus k. Okay, so this is the prime of the position vector. The magnitude of r prime can be found by the magnitude of r prime. We can easily find what's r prime magnitude. Magnitude can be easily found by this formula we have here: negative sine of t whole square plus cos of t whole square plus 1. Square or 1 is the same thing. So we will be remaining with sine square plus cos square will become 1. 1 plus 1 is 2. So we'll be remaining with this formula right here. Perfect. Now we know from here that ds of dt, that means change in the arc length over time, is actually equal to the magnitude of r prime. So we will have ds over dt is actually equal to square root of 2. Okay, now let me integrate both the sides. But before integrating both the sides, guys, I forgot something. We need to bring dt on the other side. So let me do this step here. ds is equal to square root of 2 dt, and then integrate both the sides. You'll have s is equal to square root of 2t. Perfect. When we have this, let me remove everything. When we have that s is equal to square root of 2 multiplied by t, we can always replace t by t is equal to s over square root of 2. Got it? And now what we can do here is we can reparameterize the equation, write the equation as r is equal to cos of s over square root of 2 I plus sine s over square root of 2 j plus s over square root of 2 k. Now what's the use of this equation? The use of this equation, it's better than this one, because this will actually tell you what's the actual position if you have moved a certain arc length away. But this is dependent on a particular coordinate system, whether it's a Cartesian coordinate or whether it's the polar coordinate. It depends on that. But this is not dependent on any coordinate system. It's a very independent equation of a helix. Okay, so this is what we learned. What is a reparameterizing? Now let's go ahead and let's see what's curvature. So I'll remove everything again. Okay guys, let's see what is curvature. Okay, now curvature, to learn curvature, I'll have to illustrate something to you guys. Let's say that we have these XY plane. In fact, let's make it more interesting, and let's say that I have the XYZ plane. Okay, a three-dimensional plane with the origin Z. Okay, now I have a vector. It's moving in a random direction like that. For example, at any point in this vector, obviously the vector will have a position vector. Okay, that particular position vector will have a tangent vector at any point. So this is a tangent vector, and this is called the unit tangent vector. Okay, so this is a unit tangent vector. And the unit tangent vector, since it's tangent, the unit tangent vector is first of all given by the derivation of the position vector, okay, over the magnitude of the derivation of the position vector. So that is why we know it as the unit tangent vector. It will always have a normal vector. The normal vector is always perpendicular to the unit tangent vector. The unit tangent vector is a unit vector, so the magnitude of the unit tangent vector is 1. Any vector which is having a magnitude, a constant magnitude, it is perpendicular to its prime. So the unit normal vector is actually given by. So guys, I need you to keep this formula in your mind. So whenever we are doing the next video will actually help you understanding all these, how we have put all these formula into an application. So the normal vector will be given by the prime of the unit tangent vector over the magnitude of the prime of the unit tangent vector. And obviously, as it is, the normal vector is having a magnitude of 1 because it's a unit vector. And then we have something known as the binormal vector. Okay, the binormal vector is perpendicular to both the unit normal tangent vector and the unit normal vector. So this is the general scenario that you guys can look at. Okay, so based on this, let me introduce a new concept of curvature. Okay, so curvature is actually known as how fast the curve can change direction. So the formula is given by the change in direction of the change in direction of a curve over the change in its arc length. So how fast does it change? So how fast? If the curvature is having is a curvature of 4, the curve will change direction at a higher rate than if it's having a curvature of only 2. So let's go ahead and let's see this. But this is not a very convenient way of computing curvature. I want it to be all in terms of r and r primes. So let's go ahead and let's compute. We know that k can be written as dt over dt, multiply both the numerator and the denominator by, we'll multiply both the denominator and the numerator by 1 upon dt so that the equation remains balanced. This will go as, we know the numerator is always equal to the magnitude of the prime of the unit vector over the magnitude of the prime of the position vector. Okay, perfect. Now we got this. Okay guys, now let's see something. Let's see what is known as the tangent vector. So tangent vector is given by, okay, the prime of the position vector over its own magnitude. Okay, now if we make the position vector the subject of the formula, we'll be remaining with ds over dt. If I replace this with ds over dt into r. Perfect. Now, sorry, it will be r prime. Sorry guys. Now I want to take r double prime. So from there, I'll go ahead and I'll take r double prime. When I take r double prime, I'll be left with, and sorry guys, this will be the tangent vector. Okay, when I take r double prime, I'll be left with d square s over dt e square, and the tangent vector will remain as it is, plus ds over dt over into the derivation of the tangent vector. Okay, perfect. Now I have r and I have r prime. So okay guys, now let's cross multiply these two things. Okay, Okay, so we have r obviously, and we have r prime. Okay, when we cross multiply these two things, we end up with ds over dt into the unit tangent vector cross multiplying this whole thing. So let me remove this. We have d square s over dt square t plus we have ds over dt and the prime of the unit tangent vector. Okay, now guys, this cross multiplication is distributive, sorry. So we'll do the distribution property here. So it will be d cube s over dt cube, okay? And then we'll have t into its own, obviously, into itself. Okay, perfect. And then we will have d square s over dt square is equal to into t into its own prime. Perfect. So now guys, let's analyze this. This will get cancelled. Why? Because when a vector is doing its own cross product, it's zero, because if you remember, the cross product formula is two magnitudes multiplying into the sine of the angle between them. The sine of the angle between two same vector is zero. Sine of zero is zero. Now this is one. This part only. This part is only one. Why is this part only one? This part is only one because these two are perpendicular. I told that if the magnitude of a certain vector is constant, its prime is perpendicular to it. So if you notice something, if two vectors are perpendicular, the cross product will be 1 because sine of 90 is 1. So we'll be left with d square s over dt squared. Okay, this is our, and then obviously we will be left with also, and then we will be left with, because when you take the cross product, okay, we'll be left with this particular thing. Let's not go into conclusion, and let's keep them as it is. Although I told it to be 1, let's just keep them as it is. Okay, this is the cross product. Perfect. Now let me just remove everything. And I can write down here is equal to d square s over dt square t into cross product of its own prime. Okay, perfect. Now let me just take the magnitude of the cross product. Okay guys, if you remember the magnitude of the cross product, it is very simple. Okay, I'll just take d square s over dt square, will stay as it is because it's always in the magnitude. I'll take t, magnitude of t, which is 1 because it's a unit vector. Magnitude of t prime into sine of the angle between them, which is 90, because as I told you, they're perpendicular, so this will be 1. Okay guys, so now let's move ahead and let's compute our answer that we have found. The cross product of r prime into r double prime is equal to, so this can be written as r prime square and then multiplied by, and then we'll have multiplied by t prime. Okay, so t prime can be written as this particular formula: r prime into r double prime cross product magnitude over r prime square. If you substitute this into the curvature formula, if you remember, for magnitude of t prime, we will get this formula, and this formula is only in terms of the position vector and its prime. So it's very easy for us to actually compute this particular thing. It's actually very easy this way, because we don't have to worry about finding the tangent vector, we don't have to worry about finding the normal vector. You can just compute the position vector and its prime, and we can actually get the answer. Okay? Now, this is what we have left with curvature. Okay, guys? And now let's see, using this particular formula of curvature, if we have a function which is completely depending on x and a function of x. Okay? What will be our answer? If we have a function and a function of x, the curvature formula will remain as it is. Let's just write down the curvature formula because we need to remember it. And I hope you guys are noting it down too. Okay, perfect. So let's say we have a position vector which is only depending on x as an I component and f of x as the j component, and there is no k component. Okay, perfect. So now let's go ahead and let's compute r prime. R prime, we will have I plus f prime of x j. Let's say now we will have the r double prime. In r double prime, we'll be left with f double prime of x as the j component. There will be no I component because differentiation of a constant is 0. Now let's compute the magnitude. Okay, r prime into r double prime. So r prime into r double prime, what does it actually give us? So let's say this. It's actually giving us, we have the I, j, and the k values here. We will have here r prime will be 1, f of x, and then we'll have 0. We will have 0, f prime of x, and then we'll have 0. Okay, now let's see. The I and the j component obviously will go off. Okay, the j component will obviously go off because if you cover this and cover this, you'll be left with 0. Cover this and cover this, you'll be left with 0. Now let's cover this. So what you will end up as, this thing. Because see, if you cover the k component here, perfect, yeah, and then you just cross multiply and subtract the diagonals. Okay, that will be the k component. Okay, it's a negative sign, obviously, because, not a negative sign, okay? And then, when you take the magnitude of the cross product of r prime into r double prime, you'll end up with, obviously, the magnitude of f of x prime. You'll end up with this magnitude right here, okay? Now, let's say we want to go ahead and we want to find the magnitude of r prime. So the magnitude of r prime will be the magnitude of r prime. Okay, let's see what's the magnitude of r prime. The magnitude of r prime will be 1 square plus f of x square. Perfect. This will be the magnitude of r prime. And obviously, if you input this into this formula and you put this in this formula, obviously you will get an answer which is actually in terms for a function which is actually only in terms of x and y of x. So you just have to compute this value back with the curvature formulas. Now guys, in the next video, we will focus on how this relates to acceleration, how we can use this concept to find the curvature of a helix, oscillating circles, normal plane, TNB plane of reference, and then build our way up to the acceleration concepts. Okay guys, hope you enjoyed watching this video, and please subscribe to my channel if you want more videos. If you have more questions on this video, you can obviously put them down in the comment section, and obviously wait for my next video. It will be a continuation of this topic. Thank you very much.